Hi, everybody. Welcome back. This is the second video of examples analyses using R and lavaan. In this video, we're going to talk about growth curves and fitting growth curve models. So we'll read in the data. The data is available on Canvas. It's called growth4wave.csv. Let's get a quick summary of it. We can see we now have positive and negative affect items measured at 4 different time points: positive time 1, 2, 3, and 4, negative time 1, 2, 3, and 4. We have gender 0 and 1, and then dummy-coded race ethnicity variable over here. We're going to focus on the negative affect and a little bit later maybe the positive affect items. So just as a quick note, what we're really modeling, and we're modeling that overall change, right? We talk about what is the average change are the means. So the means of negative affect from 2.08 to 1.99 to 1.88 to 1.78. We're going to model the change in those means. And so we're going to see, can we plot those? I'm going to skip past this plotting. What this will actually do is this recreates one of the plots from lecture with all the different individual trajectories on it. Instead, I want to move to talking about syntax and outcomes for growth models. So for a growth model, we say here model 97, we only specify for the growth models the intercept and the slope. So we have a latent variable that's the intercept, and as a reminder, the intercept has every item loads on the intercept. So in this case, our items are negative affect measured at time 1, 2, 3, and 4, and the loadings are fixed to 1 for every single item. So the intercept is going to represent scores on negative affect when time equals 0. Now we quantify time with the factor loadings for the slope. So we have another latent variable, the slope, and that has factor loadings for each time point as well. And where that factor loading is 0 is where the intercept is located. So here we say 0 is at time 1, 1, 2, and 3. So now we'd say, okay, the intercept represents scores at time 1, and then we see linear change from there. I'm not including anything about residuals or intercepts or anything else. We'll see. And there's a reason for that, so let me just enter this in. The reason is lavaan has a function called growth that will put all the necessary constraints for a growth model into place. So we say growth, our model and our data, and then we ask for a summary of that model. So a summary of this model, we have model fit up here. Model fit in growth curves is kind of a tough thing. It is not the most useful thing because most model fit concerns the covariance structure, the variances and covariances amongst items, whereas a latent growth curve is very focused on words are hard, the means as well. So the fit isn't always the best indicator. So down here we see our factor loadings, they're all fixed values, fixed to 1 for the intercept, 0, 1, 2, and 3 for the slope. We have a covariance. This is that covariance between the intercept and the slope. And I'll interpret this again in a second because interpretation of this depends on the values of the slope. So for intercepts and means, in a latent growth curve, we fix the item intercepts to 0 at every time. And the growth function does this automatically for us. And then we estimate the mean intercept and the mean slope. So this negative intercept here, this mean intercept, this is saying what is the average score at time 1. When time equals 0, when the slope equals 0, the average score at time 1 is 2.09. And with the p-value, we can see that's significantly different from 0. The negative slope, for every 1 unit increase in time, how does negative affect change? Negative affect goes down by 0.10, and we can see that is also significantly different from 0. And these should be the same values we saw in lecture as well. For variances, we estimate our residual variance separately at each time point, and then we estimate is there variance in the intercept and is there significant variance in the slope as well. Now this covariance up here I mentioned. As a reminder, the standardized value is the correlation. It's a pretty strong correlation. What this says is for individuals who score higher on the intercept, how are their slopes different? So it's a negative correlation. So the higher an individual scores on the intercept, the more negative their slope becomes. So the higher you are on the intercept, the more negative the slopes become. The lower you are on the intercept, the lower your score at time 1, the less negative or even the more positive your slope becomes. So now I just want to show a few other examples of what we can do with these models. So we could add in additional predictors. So now I could take the same model and say, I'm going to have gender, that 0, 1 variable, predict the intercept and the slope. See, are there differences in gender in initial score? So negative the intercept here. Are there differences in gender? What this is doing right here. Differences in gender at time 1 on negative affect. And are there differences in gender in the change in negative affect across time? So look at this model. Get a summary of this. And so a couple of important points here. So we have the regression parts here. So negative affect predicted by gender says there is a significant effect of gender. So gender 1, which I believe is girls, have higher negative affect at time 1 compared to boys. That's significant. But there is not a significant effect of gender on the slope. So it's not that boys and girls change differently in their negative affect across time. And so what I want to point out is these intercepts now, right? The intercept is the predict in a regression. The intercept is the predicted value when x equals 0, when your predictors equal 0. So this intercept and slope are now not simply the overall mean and the overall change, but the change when this predictor equals 0, when gender equals 0. These are now intercepts in that way. So they're conditional on that, and same for the variances, right? Because we have a predictor in here. These are the intercept and slope when that predictor equals 0. A couple of other examples. We can do this as a multivariate model. So we can simultaneously model both negative affect and positive affect, changing both of those simultaneously. And let's see if we can't do this without these additional constraints. So I may have to put some additional constraints in the model. Yeah, so what we have to do, the positive affect doesn't behave terribly well. So I'm going to end up constraining the residuals to be equal across time. And that's just as an example for this, for these data, because they're a little finicky. So if I look at my results now, I can see up here we've got negative affect and positive affect. So I'm going to skip the covariances for a second and come back to them. Down here on the intercepts, we have the negative affect, the intercept and slope, and positive affect. So at time 1, positive affect is 3.60. Over time, it goes up by only 0.03 points for every additional time point, although that change is significant. And here we can see there's variability in both the negative intercept and slope and the positive intercept and slope. Finally, what we have up here in covariances is we have the intercept slope covariance for negative affect, which we saw before. We have the same thing for positive affect, which again we saw before, and that's significant. So that says, you know, your level of positive affect at time 1 is negatively related. It's negatively correlated with your slope. But we also have relationships between the intercept and positive affect and negative affect, and this is basically the correlation, or the covariance right here between negative and positive affect at time 1. That's about -0.3, which we've seen throughout class. We also see correlation between the negative intercept and the positive slope. So does your negative affect at time 1 predict your change in positive affect, or is it related to your change in positive affect? And here our p-value is 0.119, so we'd say no. Correlation between the intercept for positive affect and negative slope. Is your positive affect at time 1 related to change? No, it's not. And most interestingly, potentially, is the correlation between the slopes, the positive and negative affect slope. So is your change in positive affect correlated with your change in negative affect? Here it's not, but in some other variables it may be. And these are sometimes called parallel process models because you have two growth curves change in two variables occurring at the same time, and you can see how are those changes related to each other. And so our last example I mentioned, we talked about nonlinear growth. We can, instead of saying 0, 1, 2, 3 to assume linear change. Instead, what we can do is we specify our negative intercept with factor lengths fixed to 1. And for our slope now, we only fix the first and last values, and we freely estimate these two. So this will allow that those loadings to be whatever might be of interest, whatever values might be of interest, and allow us to see, is there some sort of nonlinear trend happening here? So if we fit this model, we can see here, I'll note, I'm going to go from the bottom. This negative intercept is still the predicted score when time equals 0, so at time 1. The negative slope now represents change from 0, is a 1 unit, from 0 to 1. And if we look back here for a moment, we can see 0 to 1 is time 1 to time 4. So this represents the total change from time 1 to time 4. It means something a little bit different. What's really of interest here are these factor loadings, or negative affect at time 2 and time 3. So we would, if this were linear change, these would be about equally spaced. You go 0, 0.333, 0.6661. And we're actually pretty close to that. But we're nonlinear. Remember, these values could be anything. It could go from 0 to 1 to 1.5 back down to 1. Or it could go from 0, it could go from, you know, negative 1.5, 0, 1, anything like that. These can take on any sort of trajectory and any sort of value. And so here it looks like it's pretty linear. We can actually compare this model to our linear model. They're nested models, because in our linear model, remember, these two were fixed values, would be fixed to 0.33 and 0.66. Here they're freely estimated. So this is a nested model test. And here we can see that chi-square, that nested model test is not significant. We say there's no, the more complex model that allows for nonlinearity doesn't fit better, or doesn't, or the more constrained model, the linear model, doesn't fit worse, is a better way to say it. So that more constrained model, the linear model, doesn't fit worse, so we're going to prefer that. So here we'd say there is linear change in negative affect. I could go on and on with examples of all this. I'm going to stop right now in the interest of time, but please ask questions if you want to talk about this more. We can set up video conferences or other things as well. And that should finish us out for our longitudinal modeling lectures and examples.